My name is Dennis Davis. In this video, we'll cover correlation, simple linear regression, and other topics related to bivariate data analysis that you'd cover towards the end of a statistics course. I try to make my videos visual and fast-paced, and as with my other videos, I'll use visuals and color-coded diagrams to help make the concepts clear. Full disclosure, I'm an engineer, not a mathematician and not a statistician, but I know the material and I'm sure this video can be helpful to you. I try to make videos I wish I could have watched when I was a student, but there was no YouTube and no internet. I hope they benefit you. Outline in the left panel, vocabulary words and phrases in yellow. In this video, I'm going to temporarily jump into the middle so you can see where we're heading. Then we'll jump back out and start at the beginning, build a thorough foundation, and progress in an orderly fashion towards the learning objectives. I think it helps make early concepts clearer if you know the destination before we start. So, here's the big picture. Correlation and simple linear regression are statistics topics under the broader category of bivariate data analysis. The word bivariate means two variables. Your statistics class will start with the analysis of just one variable at a time, but by the end you'll be looking at more than one. And to illustrate where we're going, I'll start with just one variable. Our sample scenario is that we're moving to a new town called Newtown, and we want to know what price we can expect to pay for a home there. All we have is a sample consisting of these 6 randomly selected sales prices from last month. I'm inventing a unit of measure called K dollars that means $1,000. So, just to be clear, the first sales price in the list, $271.7 K dollars, means $271,700. We can plot the data on a number line to get a visual representation of the price distribution. And for reasons that will make more sense later, I'll flip the axis up to be vertical. Of course, it still tells us the same thing. So, here's the big question. Based on these sampled prices, what should a home buyer expect to pay for a home in Newtown? Or, to ask the same question a different way, what's the predicted price based on this sample? In order to make a prediction, we need a mathematical model. Well, we don't have much information, so our model is going to be pretty simple. Our best prediction would be the average of these 6 sales prices in the sample. As you know, to find the average, we add up all 6 prices, then divide by 6, and we get 418.0 K dollars. In statistics, we denote the mean or average of a variable's value by putting a horizontal bar over the variable letter. Since I flipped the sales price up vertically, we'll call it the Y variable. So the mean value we found, 418.0 K dollars, is Y bar. So, based on all the information we have so far, which isn't much, we can expect to pay about $418,000 for a new home in Newtown. And here's the average marked on our vertical number line. So when we have one variable, our prediction model for the next variable value is simply the average or mean of the values we've encountered so far. But now let's consider a second variable, so that for each home value we also know the square footage of the home. When both variables are numeric, we can graph the points on a two-dimensional diagram called a scatter plot. Let me clear a little room and show these data points in 2 dimensions. Each point on the graph represents 2 variable values simultaneously. The first point is lined up with 1,701 square feet on the horizontal axis and 271.7 K dollars on the vertical axis. So each point corresponds to a distinct home sale and simultaneously represents the value of 2 distinct numeric variables that describe the sale: home size and sale price. Without too much difficulty, you should be able to see that the data points show an upward pattern. If a straight line can be drawn relatively near to the data points, like this, we say the 2 variables have a linear relationship, and, importantly, the straight line becomes our new prediction model. Let me say that differently. Knowing the values for a second variable can help us improve our prediction model from y hat. to something better and more descriptive if the data has a linear relationship. It might help in understanding linear relationships to see a few examples of data that isn't linear. Here's a data set that's nonlinear. It looks like interesting data, but there's a clear curve, so a straight line would not describe this data very well, and a straight line model would result in bad predictions. Here's another example. Again, it's perfectly good data showing a real and interesting relationship between two variables, but it's not linear, so a straight line model wouldn't fit the data. This video's topics of correlation and simple linear regression apply only to data sets when there is, more or less, a straight line linear relationship, like in our home sales example. Let me review some ways we refer to the x and y axes because they're described by some insightful terms. Sometimes x is called the independent variable and y called the dependent because y depends on x. When we write y equals f of x, we're saying that y's value depends on x's value. Similarly, the descriptions input and output can be used, especially in computer science. In regression and statistics, you'll often see x called the predictor variable or the explanatory variable, to which y is the response variable. And in machine learning, x variables are called features, and the y variable is called the target. Please don't be confused or alarmed when you hear the x and y axes called different things. X and y are okay to use. If you're in STEM, then you'll hear independent and dependent a lot. The others are more specialized. Okay, in this video, we'll work towards answering 4 important questions about bivariate data. First, are the two variables related? That is, does increasing or decreasing one tend to correspond to an increase or decrease in the other? If so, how strong is the relationship? Is it a tight, consistent relationship like this? Or a loose, scattered one, like this? How can we quantify the strength? Remember, before we added our second variable, our best prediction for the expected value was simply the mean of our sample values, y bar. Now that we've added our second variable, can we use it to make a better prediction? What if we knew a home was 2,180 square feet? With the second variable, can we make better predictions than y bar? And lastly, how good is the prediction? The first 2 questions fall under the topic of correlation. The last 2 are under linear regression, or more specifically, simple linear regression, since there's only one explanatory variable. The topics are tightly related because mathematical concepts we develop for correlation will be used to make linear regression simple. When I studied probability and statistics in high school and college, I learned a lot of things, but at the time, I didn't always see how it all fit together, and that would have made everything so much clearer and easier to understand. So let me finish up this introduction by showing how these topics fit into a statistics class. Here's an outline of a typical probability and statistics class. Different textbooks and instructors might have slight variations, but this is a basic outline. And here's the topic of this video: correlation and simple linear regression. These topics I'm showing in blue are considered descriptive statistics. They might be covered in a one-semester course named Statistics, Elementary Statistics, or even Descriptive Statistics. The topic of probability is shown in green. It could also be its own one-semester class, and the number of topics is a lot more than I'm showing. There just isn't room to show everything. So please don't think probability is just 3 rows worth of material. So, descriptive statistics and probability are completely different subjects and can be taught separately, but they're often taught together because they're both needed as the foundation for the capstone topic of inferential statistics. So you might encounter a year-long probability and statistics class that covers both descriptive statistics and probability that would include inferential statistics at the end. I have a 3-part series on inferential statistics. If you're in a probability and statistics class or an interested self-learner, you might find them helpful. I'll put the playlist link in the description. I think they're some of my best videos, but not many people watch them. So, our topic of correlation and linear regression is part of descriptive statistics. Specifically, it's a subtopic under bivariate data analysis, and more specifically, when both variables are quantitative, which means numeric. We'll cover all the details. I just want you to be able to see how the subject fits into the bigger picture. Since correlation and linear regression are some of the last topics covered in a statistics course, I'll review some important concepts from earlier in the class, starting with levels of measurement, specifically qualitative and quantitative variable types. There are 4 levels of measurement that describe the nature of different kinds of variables: nominal, ordinal, interval, and ratio. I'm not making them yellow since they aren't vocabulary words for our topics, but you'll learn them in your statistics class. For our home sales example, the 2 variables we've mentioned are price and square footage. Sometimes I think of variables as tags tied to a person or object that describe it. Here are 2, but there are hundreds or even thousands of possible variables that can describe a home sale. The 4 levels of measurement are ways to categorize different kinds of variables. You'll cover the details of each level in your statistics class, but for the purpose of this video's topic, we can broaden the categorization further to just qualitative and quantitative variables. Qualitative variables are simply names or labels. A home's exterior could have the values brick, wood, vinyl, or stucco. The energy rating could be a number of stars. The condition could be excellent, very good, good, and so on. In short, we don't try to do math on qualitative variables, since they're just labels. Some other examples of qualitative variables are colors, freshman, sophomore, junior, senior, Toyota, GM, Honda, Ford, smoker, non-smoker, and male, female. A good rule of thumb to remember is that we don't try to do math on qualitative variables. That's why energy rating is qualitative, even though it looks like a number. We don't do math on the number of stars. Same with zip code, a common example. In the US at least, it sure looks like a number, but we don't do math on them, so zip code is a qualitative variable. On the other hand, quantitative variables are numeric that we can do math on. So these 5 examples are all quantitative. By the way, dates are considered quantitative because we can put them in order and add or subtract to get intervals of time between dates. Most attributes that we measure or count are quantitative data types. Physical phenomena such as distance, mass, temperature, pressure, energy, or force. Also, amounts of money are quantitative, as well as things that we count, such as number of bedrooms, number of pets, children, automobiles, and so on. Basically, if it's a quantity, then it's quantitative. Because, in English at least, the words qualitative and quantitative are so similar, we sometimes call them categorical and numerical, respectively, to avoid confusion. I remember in school, I knew clearly the difference between qualitative and quantitative, but I would still sometimes say one when I meant the other. I'm not sure why. So, I'll try to use categorical and numerical. It's pretty common usage, so you should know all 4 terms. And if your instructor has a preference, please agree with your instructor. Okay, the next topics to review on our statistics outline are population, sample, mean, variance, and standard deviation. A population is the set of all people, things, or events that we want to know something about. Members of the population have attributes, either categorical or numerical variables, that we want to evaluate and analyze. When a population consists of people, it might be all the voters in a state, or all the women attending a certain college, or all the patients with a particular disease. In English at least, the word population is often associated with people, like when we refer to the population of a city or state. But in statistics, populations can also refer to things or events. Some populations consisting of things are all computer chips made at a factory, or all the books in a library, or all the homes recently sold in Newtown. Some populations consisting of events might be all the traffic accidents at a particular intersection, all the McDonald's drive-through orders for a week, or all the daily trades made on a stock exchange. So, we want to know something about a population, but it's often too expensive, impractical, or even impossible to evaluate every member of a population to find out the values for their variables. So, in statistics, we evaluate a sample. A sample is a subset of the population that, hopefully, represents it well. Since a sample is usually much smaller than the population, it's easier to collect data, that is, variable values, on the members of the sample, since there aren't as many. Then we work backwards to infer what we want to know about the population based on what we see in the sample. This is what inferential statistics is all about. In statistics, we say very specific things about the characteristics of populations and samples in terms of each other, so it's very important to use correct terms and symbols. These are the characteristics we'll be using for correlation and linear regression: mean, variance, and standard deviation. And these apply only to quantitative or numeric data types. Categorical variables won't have means, variances, or standard deviations. When describing populations, these characteristics are called parameters. When describing samples, they're called statistics. They're easy to remember because parameters describe populations and they both begin with P. And statistics describe samples and they both begin with S. I think these terms will make more sense as we proceed. The mean of the population is represented by the Greek letter mu, so mu is a population parameter. It looks like a lowercase u with a tail in front. In math and science environments, we usually say the M sound followed by the word u, so it rhymes with few. Occasionally you'll hear mu, which sounds silly to me, but you can make life easier on yourself by using the pronunciation your instructor uses. Mu is the population mean or average, whose formula looks like this. I'll be using a mixture of blue and orange on this chart for variables and their characteristics, just so we get used to it. I'm going to assume you're familiar with summation notation and know that this symbol means add up this list of numbers. If you're not familiar, I've linked to some good videos in the description. Here, capital N is the size of the population, and that's how many numbers we're adding up, one variable value for each member of the population. So I'll add N to the chart as population size. It's not yellow because size isn't exactly a vocabulary word, but you should know the symbol for the sizes of the population and sample, and the symbol for the population size is capital N. So, like you'd expect for the mean, add up all n of the blue variable values and divide by n. And that's mu, the population mean. Again, the population is often just too large or unwieldy to know every x value, so we don't really know mu very often. But if we could, here's how we'd find it. You might see an abbreviated, simplified form of summation notation without the index or subscript reference. It means the same thing. Add up all the x values and divide by n to get the mean. It's just shorter and less formal. I'll use this shorthand later in the video. The sample mean has the symbol x bar, or y bar if we're using the letter y to refer to the variable. The bar means the average value of the variable, and x bar is a lowercase x with a bar on top. The sample mean is a statistic since it describes a sample. One more quick review: mu is a parameter because it describes a population. X bar is a statistic because it describes a sample. The formula for a sample mean is almost exactly the same as for the population mean, except it uses lowercase n instead of uppercase n. Lowercase n is the symbol used for sample size. It's easy to remember. Populations are bigger than samples, big N for the big population size, small n for the smaller sample size. When talking about the mean of a population, we use mu. And when you see the letter mu, you'll know it's a reference to a population. Likewise, use x bar to represent the sample mean, and when you see x bar, you'll know it's a reference to a sample, not a population. It's important to use the correct symbols to denote precise meanings. Next is the population variance, whose symbol is the lowercase Greek letter sigma squared. Sigma looks like a small letter O with a rightward stem on top. The idea behind the variance is simple. I'll illustrate it down here. For simplicity, let's consider a very small population. A family's 3 children, and the variable we're interested in is their Saturday screen time in hours. The variable values are 2, 3, and 7. I'm using orange this time. Later, when we look at 2 variables at the same time on a scatter plot, using 2 colors will be helpful. But for now, it doesn't matter, blue or orange. This one's orange. In order to find the variance, we'll first need to know the mean. Here's the formula for population mean, and the population size, capital N, is 3. Let me say again that most populations are a lot bigger than this. In fact, they're often so big we can't measure all the members. So I'm showing a very small population just to illustrate the idea and the math behind the variance. We need mu, so we add up all 3 variable values and divide by 3. 2 plus 3 plus 7 is 12, divided by 3 is 4, so mu is 4. We're going to evaluate each point's distance from the mean. But first, let me pivot the data vertically. It'll work either way, but for regression, I think it'll look more familiar later if we turn it up like this. To find the variance, we start by taking each point's distance, or difference, from the mean mu. This point 7 is plus 3 away from mu. 7 minus 4 is 3. The data point 3 is negative 1 away, and the data point 2 is negative 2 away, as these arrows show. We need all these differences to find the variance sigma squared. By the way, these differences will always add up to 0, since the mean mu is the number that balances them out. Now, to find the variance, we square each of these differences. Now they're all positive, and we find the average of these squared values by adding them up and dividing by 3. And that's the variance. So, sigma squared is 14/3, which is 4 2/3. I'll talk about the units in just a moment. So in plain language, the population variance, sigma squared, is the average squared distance between each point and the population mean mu, just the average of the squares. One way to visualize this is to imagine lines from the mean out to each point, and then drawing or imagining actual squares having that side length. The variance is the average square size, sigma squared. Here's the formula. It looks more complicated than the simple idea, but you can see that it's the average of the squared differences. I think a lot of times in math, a formula looks more complicated than the simple idea it represents. So as you study math, keep this in mind. Figure out the simple thing the formula is telling you, and don't be intimidated if a formula looks complicated. Behind every complicated-looking formula is a simple idea, and the simple idea behind this formula is the average of the squared differences. Also, notice here that the formula for variance includes the mean. This shows that to know the variance, we must first know the mean, since the variance is the average squared distance from the mean. If you don't know the mean, you cannot know the variance. Okay, now for the units of variance. When we subtract here to find the difference, the units are the same as the variable. Since the variable is screen time in hours, hours minus hours is hours. But then we square this quantity, so the final units turn out to be hours squared, and the variance of this population is 4 2/3 hours squared. The units of variance are always the square of the unit of the variable. This can result in unusual or non-intuitive units that don't have a clear physical meaning, like hours squared. If we're measuring income in dollars, the variance will be dollars squared. Or counting children in a household, children squared. It sounds like nonsense, but the squared units arrive purely from the mathematical definition of variance, not because they have any practical physical interpretation. So it's a byproduct of the formula, not a meaningful unit on its own. On the bright side, it's easy to associate the squared units with the symbol because the symbol for variance is sigma squared. To get back to units that are more meaningful and tangible, we take the square root of the variance. This yields the standard deviation, whose units are the same as the data, and whose symbol is sigma, not squared. So the standard deviation is the square root of 4 2/3 hours squared, which my calculator tells me is about 2.16 hours, not squared. While square roots can be positive or negative, we never consider the standard deviation to be negative. Let me illustrate relative variances. Suppose our population was 12 exam scores for a tough exam, the first exam of the semester. 12 is kind of a small population, but we're just illustrating concepts. Also, it's just one variable, so the display is a dot plot instead of a scatter plot. Here are the scores, and their mean mu is 70. Now, here are the 12 scores for the second exam. Their mean mu is also 70, but can you see how the scores for exam 1 are more spread out than exam 2? The scores for exam 2 are more tightly clustered around the mean, and the scores for exam 1 are more spread out, even though the two means are the same. Variance and standard deviation tell how spread out the data is around the mean, and higher values mean more spread out. Okay, so there are two gaps left on our chart, the sample variance and standard deviation. I'll show the formula for sample variance, which closely resembles the formula for population variance, sigma squared. The symbol for the sample variance is s squared. This one's blue, but the colors don't matter for now. Naturally, we reference the sample size, lowercase n, rather than the population size, capital N, and the difference we square are between each point and the sample mean, x bar, instead of the population mean, mu. We don't know the value for mu, so we use x bar instead. But the feature in the formula that causes the most confusion is that we divide by n-1 instead of n. The reason is that samples tend to have less variation than the populations from which they were drawn. Let me illustrate with an example of a much bigger class taking a tough exam. Here's how the 198 scores are distributed. Scores near the mean are common. Extremely high scores and extremely low scores are less common. And we take a random sample of 5 scores and plot them. A random sample will usually, but not always, have less variance than the population from which it was drawn. I was tempted to go into detail, but considering that we're still reviewing statistics and haven't even started correlation or linear regression yet, I decided to just keep the explanation simple. In statistics, we want the sample variance to reflect the population variance. So to bump it up a bit, we divide the squared differences by the sample size -1 rather than the sample size. Reducing the denominator makes the sample variance computation for s squared a little higher, so in the long run, it will more closely reflect the population variance sigma squared. The sample standard deviation is, of course, the square root of the sample variance and has the symbol s. So you should be familiar with this chart. Parameters describe populations and are usually Greek letters. Statistics describe samples and are Latin or English letters. In real life, we never know a population's parameters. We use a sample statistics to help us make inferences about them. That's what inferential statistics is all about. However, if you're studying in school, your instructor is likely to present small data sets and tell you their populations, just like I did, to be sure you know the correct vocabulary and symbols to use. Before we start talking about bivariate data analysis, let me talk about some notation for sample statistics that will be very important later. It's called sum of squares, or SS notation. Let me take the numerator of the variance formula and write it down here. I'll leave off the I index for brevity. It still means the same thing. Add up all the squared differences. The leading symbol means sum, and of course the superscripted 2 means squared. And what we're squaring is the difference we get by subtracting two numbers. The pattern sum of squared differences occurs a lot in statistics. It occurs so often that it's borderline funny. It might be a great way to help your learning and understanding to see the humorous side of what I'm saying. Statisticians, it seems, love to find the difference between two numbers by subtracting, squaring those differences, and adding them up. If you're a carpenter, you hammer nails. If you're a nurse, you take blood pressure. And if you're a statistician, you sum squared differences. It's just what you do. We see it here in the calculation of the variance and the standard deviation, of course, since it's just the square root of the variance. And we'll see it several more times later. It happens so often that even the statisticians are in on the joke, and they have a shorthand for it. SS stands for sum of squares. Then we add a subscript to denote the difference variable. The subscript x means x sub I minus x bar. So these two expressions mean the same thing. The right expression can be read out loud as sum of squares x, SS sub x, or even SSX. I'll use sum of squares x. It's a little longer but more descriptive, so better for learning. When referring to the y variable, it's sum of squares y. I remember making the mistake in college of thinking the variance was sum of squares x. I didn't divide by n minus 1. Just understand what each symbol means, and putting the formulas together will be easy. Since the variance is the average sum of squares, we take the total sum of squares and divide by n minus 1 to find the average. And so the sample variance of x can be written as sum of squares x over n minus 1. N minus 1 instead of n, remember, because sample variances tend to underrepresent the variance of their population. So to find sample variance, we divide sum of squares x by n minus 1 to bump it up. Everything is much easier if you understand what things mean instead of just trying to memorize formulas. That's true in all of math and engineering. You may also see the variance of x written in function notation like this, which can be read out loud as variance of x, var of x, or even var x. Variance is such an important idea in statistics that here we have 4 ways to represent it: the symbol, the computation, the shorthand, and as a function. Let's work out a numeric example. In practice, computers will do the math for us, so these computational skills are not vital to develop. But understanding the meaning behind the concepts can help us see the big picture and how the parts fit together. If you had a sample consisting of hundreds or thousands of observations, you wouldn't want to do these calculations without a computer. But it's a good idea to know how to do them with a small sample. We'll use our small sample of 6 home sales, and our variable will be sales price. The unit of measure will be K dollars, which means thousands of dollars. Here are our 6 data points. We'll find the mean, variance, and standard deviation. Here's the formula for the mean. Sum them up and divide by how many. The sum is 2,508.0 K dollars, and when we divide by 6, we get x bar equals 418.0 K dollars. Now we need to find each point's difference from x bar. That's why we find x bar first. So we'll add this column for x sub I minus x bar. Then we'll need to square this difference, so here's a column for x sub I minus x bar squared. I'll add the units on top. For the first point, x sub I is 271.7 K dollars. X bar is going to be 418.0 K dollars for every point. So 271.7 K dollars minus 418.0 K dollars is negative 146.3 K dollars. Then for the next column, we square this number. We get 21,403.7 K dollars squared. I'll just carry 1 decimal place. Then we continue for the other 5 points, the difference between each point and x bar, and then squaring that difference. It's not important to the math we're doing, but I want to draw your attention to this value that's very small compared to the others. I'll circle it in purple and point it out again in a few minutes. It's small because its variable value, 416.9 K dollars, is very close to the mean, 418.0 K dollars. Okay, the sum of the squared differences that all the statisticians seem to like is SS sub x, sum of squares x. We add up the squares and get 64,275.4. The units, remember, is K dollars squared. We want the variance, and the sample variance is sum of squared x divided by n minus 1. The sample size n is 6, so we divide by 5 to get 12,855.1, and the units are still K dollars squared. Finally, the standard deviation is the square root of the variance, which is easy to remember since s is the square root of s squared. The square root of 12,855.1 is about 113.4, and since we took the square root, the units are back to k dollars. So, given a small numeric sample, we know how to find the mean, variance, and standard deviation. Here's another small sample for you to try if you like. The 6 home sizes that correspond to these same 6 sales prices. I'll show their mean, variance, and standard deviation in a few seconds, but you might want to pause and figure them out on your own. A little effort now will build your confidence. Here are the statistics. Mean x bar, variance s squared, standard deviation s. As I said earlier, computers usually do the tedious work for us, and I'll show you briefly that Excel, for example, has these functions built in. You can use Google Sheets also. We enter or import our data into these cells. Then to find the mean, variance, and standard deviation, we use these Excel formulas. Please notice the .s in the variance and standard deviation function names. The s denotes sample. var.s will return the sample variance by dividing the sum of squares by the sample size minus 1. We don't have to tell Excel the sum of squares or the sample mean. It figures out everything it needs based on the data set. In the unlikely event that you're working with data from an entire population, use var.p to return the population variance. Excel will divide the sum of squares by the population size, capital N, and won't subtract 1. Same with the standard deviation function. And one more reminder, if you are dealing with a population's data, then the symbols in row 10, 11, and 12 would be parameters mu, sigma squared, and sigma. And that's our review of populations, samples, mean, variance, and standard deviation. And now we're ready to talk about bivariate data analysis, which is where we find the topics of correlation and linear regression. Bivariate data analysis is about exploring the relationship, if there is one, between two variables. Bivariate, two variables. We already know that the members of our population can have many variables. When we conduct bivariate data analysis, we're examining the relationship between two variables at a time. This means there are 3 combinations of variable categories. Both variables can be categorical, one can be categorical and the other numerical, or both can be numerical. The combination of variable types determines the possible methods we can use to visualize and analyze the data. For correlation and linear regression, we're only interested in the bottom combination, but for the sake of completeness, let me provide a quick review of the first two. When both variable values are categorical, we can create a two-way table. Here's an example of a display containing 2 categorical variables for college students. Their college class across the top margin, freshman, sophomore, junior, senior, their categories. And their housing type in the left margin, also categories. That's why it's called a two-way table. Each cell number tells how many students are described by the combination. For example, 19 juniors live in a dormitory. Two-way tables contain totals in their right and bottommost margins. Just add across and down. So our study included a total of 111 sophomores, and a total of 31 students who live in fraternities, and a grand total of 405 students. There's a lot of information on a two-way table. As an aside, you may also see two-way tables called contingency tables. I just don't want it to seem strange when you encounter it, and it's a more common name when studying probability. Not a big deal, and I won't mention it again. Two-way tables can be displayed as a clustered bar chart. All the numbers from the two-way table are on this chart, but the chart also helps us visualize the relative sizes of each group and segment. The two-way chart and this graphical depiction are really the same thing, an analytical summary of 2 categorical variables. You'll cover two-way tables in a statistics or probability class, and we won't go further in this video. The next combination of variable types is one categorical and one numerical. To display this relationship, we use stacked one-variable plots. For example, if we had just one numeric variable, we could use a dot plot like this. This plot should look familiar. I've been using dot plots to show exam scores and screen times. In this example, the vertical gray number line denotes the numeric axis. Now we can add a new categorical variable and stack it back to back next to the first, like this. This lets us compare and analyze numerical data from two different categories. Now hear sirens. Alternately, we could draw a box and whisker plot like this. Here the gray number line is horizontal. I'm not going into details of box and whisker plots. It's a topic you'll cover in a statistics class. Now, when we add a categorical variable, each category value gets its own version of the single variable numeric plot, and we display them side by side to get a sense of how the categories compare to each other. There are more ways to display categorical versus numerical data, and most of them include single variable numeric plots, like a dot plot or box and whisker plot, and then stack a similar plot nearby for each category so they can be compared. The third combination is when both variables are numeric, and we use scatter plots to display this data. We've already seen scatter plots in the beginning of the video when we jumped ahead to get a preview. A scatter plot puts each numeric variable on its own axis, and every member of the sample has a point in the plane with coordinates corresponding to its variable values. And that's a scatter plot. Both variables must be numeric. A scatter plot is the lab bench where we examine the relationship between two numerical variables using tools like correlation and linear regression. This is important. All of our work, all of our formulas, and all of our math will be anchored right here on this type of diagram. And with that introduction and background, we are finally ready to begin. Here's some home sales data again, and here are the data values we've been using in our statistics calculations. On a scatter plot, we're seeing data for two variables at the same time. As we've already seen, each point represents a home sale having two simultaneous variable values, home size and sales price. I'm going to formalize the blue and orange color coding going forward. Blue in general will represent the independent variable on the x-axis, and orange will be the dependent variable on the y-axis. All the work we've done so far can be visualized on the scatter plot. The mean home size for this sample of 6 is 2,767 square feet here, and we'll label it X bar. And the mean sales price is $418.0 K, orange Y bar here. The variance of X is the average of these distances squared. So it's easy. The variance of X is the average area of these blue squares. Now, I'm drawing squares to show you what the formulas mean because they have such a clear physical interpretation on the scatter plot. But it's mostly a learning aid because statisticians don't draw actual squares. So when you do homework or test problems or do bivariate data analysis for your job, you can imagine these squares to help remember the formulas. But no one's going to expect you to actually draw squares on your scatter plot. In fact, unless your instructor or a homework problem asks you to draw squares, the only time you'll ever do it is when you're teaching someone else what these formulas mean. And the formula for variance means the average square size, the sum of the squared differences over n minus 1, which is SS sub x over n minus 1, same thing. Again, we divide by 5 instead of 6 to find the average, since our data is from a sample. And we know that the standard deviation, S, is just the square root of the variance, S squared. The variance of Y is the average of these orange distances, squared. It looks like 5 squares instead of 6 because the square for this point is too small to see. It's the small squared difference from earlier that I emphasized was small compared to its neighbors. So all the numbers and formulas we've covered can be visualized right here on the scatter plot. If you can see a formula's picture in your head, then math can be a rewarding adventure in understanding rather than a worrisome exercise in memorization. And this is especially true for correlation and linear regression, because the scatter plot is the perfect backdrop for visualizing all the formulas. Okay, now for some vocabulary. There's a point on a scatter plot at the intersection of the two means lines. Its coordinates are, of course, x bar, y bar. I'm marking the point with a red square so we don't confuse it for an actual data point. It has a few acceptable names: the point of averages, the mean point, or the centroid. They're all pretty descriptive, so it should be easy to know them all for a class. When we reference it later, I'll use centroid, but you should use whatever term your instructor uses. Next, if there's a relationship between two numerical variables, then we'll see a pattern in the scatter plot. We've already seen two patterns or trends in our preview: upwards and downwards. The trends tell us that the two variable values vary together. In other words, they co-vary. And our next vocabulary word is covariance. Covariance is a measure of the covariability between two variables, and it can be positive or negative, or maybe zero. Let me warn you that covariance by itself doesn't tell us very much, but it's a core building block to several other important statistics, including two more we'll cover in this video. So it's very useful in formulas, but not that useful by itself. Let me build the formula for covariance, and then we'll see what it means. As you might expect from the name, covariance is a lot like variance, except we have two variables instead of one. Here's the formula for the variance that reflects the spread outness of variable x about its mean. It's still the average of the squared differences between each variable value and the mean of the variable values. We've seen this lots of times. Of course, we could abbreviate and write the numerator as sum of squares x. Since we have the sum of x sub I minus x bar squared, let's write it out as the sum of x sub I minus x bar times x sub I minus x bar. Same thing. And these are still the same, sum of squares x. Now, I'll write the same formula for the other variable, the orange y variable. Of course, it references y sub I and y bar instead of x. Now, before we proceed, we have two expressions, both labeled s squared, but they're different, so they should have different symbols. When dealing with bivariate data sets, it's common, actually expected, that symbols for statistics will have subscripts like this to denote which variable the statistic describes, x or y. S sub x squared is the variance of variable x, the spread outness in the horizontal x direction. S sub y squared is the variance of variable y, the spread outness in the vertical y direction. So please don't think these are new or different symbols. They're just more specific. The subscript simply tells us the direction of the variance, horizontal x or vertical y. So how can we get the covariance of the two variables? Well, we just mash these two equations together. So instead of multiplying blue difference by blue difference, or orange difference by orange difference, we multiply blue difference by orange difference. And that's the covariance, which is essentially the merged variance for two variables instead of one. Let me point out again that the numerator for the x variance is sum of squares x. The numerator for the y variance is sum of squares y. And that brings us to the numerator for the covariance, which we write as ss sub xy, which is sum of squares xy. On one hand, it's clear because the subscript includes both variables as a reminder that we're multiplying the differences of both variables. However, it's a tiny bit tricky because remember that ss stands for sum of squares, and we're not really squaring anything. Instead of squaring the x differences or squaring the y differences, we're multiplying the x difference by the y difference. But we still use the symbol ss sub xy, sum of squares xy, as the numerator of covariance to follow the pattern. The ideas are so similar that they decided to use the ss symbol even though it's not technically a sum of squares. Okay, let's do a computational example and calculate the covariance of our home sales data. Here's the scatter plot with the centroid marked, and as a reminder, here's the covariance formula. Let's consider this point. To find the x variance, we found the average area of the 6 blue squares. I'm just drawing one. To find the y variance, we found the average area of the 6 orange squares. Now, to find the covariance of x and y, we're going to find the average area of these 6 rectangles. Each rectangle's area is a product of this distance, x minus x bar, times this distance, y minus y bar. How interesting! So the x and y variances depend on summing and averaging squares, and the covariance of x and y depends on summing and averaging rectangles, one side of each length. But we still use SS sub xy, sum of squares xy. Here's how the calculation works out. Here are the x and y variables we've already seen, the blue home size x and the orange sales price y. Here are their sums and averages. We calculated them earlier. Here are all the x minus x bar values and the y minus y bar. And to find the covariance, we don't square blue or orange, but we multiply them together. The sum of squares xy, is 460,090.5. To find the covariance, we divide by 5 to get 92,018.1, and that's the covariance. If you ever have to calculate variances or covariances manual for a homework or test problem, building a grid like this is a good strategy. Label your columns and keep everything organized. Covariance is pretty simple. Actually, with practice, understanding, and confidence, everything in this video is pretty simple. Have I mentioned yet that everything can be visualized on a scatter plot? I think I have, and I probably will again. Here's a variance and covariance summary chart. The first row has formulas and symbols for the variance of x, the variance of y, then covariance of x and y. This table introduces a new functional notation for covariance, COV. The arguments are the two variables, so this is the covariance of x and y. You're likely to encounter this notation since there isn't really a symbol for covariance like these for variance. I want to include our visual memory aids. The variance of x is based on the squared x differences. The variance of y is based on the squared y differences. And the covariance of x and y is based on the x difference times the y difference, and our memory aid is a yellow rectangle. A worthwhile goal is to be able to replicate this chart from scratch. Of course, I would encourage you not to memorize it, but rather understand what each statistic means and be able to build the chart from that understanding. Now, I want to dive a little deeper into the numerators of these statistics, the sum of squares parts. The shorthand for the numerator of the variance of x is SS sub x, which is shorthand for sum of squared x differences, x minus x bar. The memory aid is a blue horizontal line denoting x minus x bar. Then we square it. And it's exactly the same for the numerator of the variance of y. The numerator of the covariance is the product of the x and y differences, and the SS notation has a subscript x and y for each factor. The memory aid is a yellow rectangle because in the covariance numerator we're adding up rectangles instead of squares. For sum of squares x and sum of squares y, the subscript answers the question, what's being squared? X means x differences are squared, y means y differences are squared. It's perfectly clear. But there's a missing symmetry because in the numerator of the covariance, SS sub xy has a subscript for each factor. Likewise, the formulas for variance have two factors, but their sum of squares shorthand has only one subscript. So you may see the shorthand for sum of squares x written with two x subscripts like this, SS sub xx. So sum of squares x equals sum of squares xx. It's two slightly different notations for the same thing. And you may see the shorthand for sum of squares y with two y's like this. Again, it means the same thing. It's as if one person said, hey, sum of squares xy has two subscripts, so shouldn't sum of squares x and sum of squares y also have two, so they all three match? And somebody else said, well, I guess if you want. So there we are. Both ways are fine for sum of squares. My advice is to use the notation your instructor or textbook uses, and don't be confused if you see it the other way. And once more, because I made this mistake in school, please don't think this is the formula for covariance, or that these are the formulas for variance. These are all sums of squares, the total areas of squares, or rectangles. Variances and covariances are average areas, so they are sums of squares divided by n-1. It's better to understand concepts than to try to memorize formulas. If you understand what's going on, you can figure out the formulas, but if you don't understand concepts and then forget or misremember a formula, you're stuck. Excel has covariance functions for samples and populations. Covariance.s for samples and covariance.p for populations. They take two ranges as arguments, the x range and the y range. The functions do all the math and just return the covariance. And the covariance for our home sale sample dataset is 92,018.1 square feet K dollars. If you're using another statistical software package, it's a worthwhile exercise to be sure you can enter or import some data into it and repeat the calculations we're performing. It's important to point out that switching the x and y variables won't change the covariance, so the covariance of x and y is the same as the covariance of y and x. That makes sense. Both ways they're the exact same yellow rectangles, just twisted around on the scatter plot. And the covariance is just the average yellow rectangle area. So, I said earlier that covariance by itself doesn't tell us very much. It is important because it's a factor in some of our future formulas. When we analyze two numerical variables on a scatter plot, we're striving to answer these questions, and the first, are the two variables related, is kind of answered by the covariance. Let me draw a line that represents the trend of the data. We'll be able to describe the characteristics of the best fit line during the next chapter of this video on regression, but for now, let's just assume this line represents the trend. If the covariance is a positive number, then the variables have at least some degree of an upward pattern denoting a positive correlation, so the trend line has a positive slope. If covariance is a negative number, then the variables have at least some degree of a downward pattern denoting a negative correlation, so the trend line has a negative slope. Let's understand why a positive or negative covariance corresponds to a positive or negative slope by going back to our home sales data set. Here are the lines for x bar and y bar, and their intersection point is the centroid, which will be at or near the middle of the points on the scatter plot. So the two mean lines divide the scatter plot into 4 quadrants. When a data set has an upward trend, it will tend to have more data points in this quadrant and this quadrant. That's what gives it an upward trend. From left to right, it goes up. In the upper right quadrant, each data point is to the right of x bar and above y bar. So the numbers we multiply to get our yellow covariance rectangles are both positive, and x minus x bar times y minus y bar is greater than 0. And in the lower left quadrant, both differences are negative. But since negative times negative is positive, the product x minus x bar times y minus y bar will also always be greater than 0. So the yellow covariance rectangles for data points in these two quadrants contribute positively to sum of squares xy. Well, you can probably see where we're going. In these two quadrants, one difference is positive and the other is negative. So these products will always be negative, and the yellow covariance rectangles for data points in the two red quadrants will contribute negatively to sum of squares xy. So when two variables have a positive correlation, most of the points will be in the two green quadrants since the data points have an upward trend, and the many positive rectangles in the green regions will outweigh the relatively fewer negative rectangles in the red regions. And the total sum of squares xy will be positive. And dividing by n-1 to get the covariance doesn't change the sign, so the covariance will also be positive. When a data set has a downward trend, most of its data points will be in the two red quadrants, since the data points have a downward trend. And their many rectangles will outweigh the relatively fewer positive rectangles from the green quadrants, and the sum of squares xy will be negative. And dividing by n-1 to get the covariance doesn't change the sign, so the covariance will be negative. So that's why a positive covariance means a positive correlation, and a negative covariance means a negative correlation. When there's a lack of a trend due to symmetry between the quadrants, the positive and negative covariance rectangles will cancel out and result in a sum of squares xy that's 0 or nearly 0. So that's how covariance could be 0. Now we're going to convert covariance into something else, something much more useful called the correlation coefficient that will answer our second question, how strong is the relationship, and provide a more precise answer to the first. This transformation will make more sense if you follow the reasoning. We'll start with looking at the units of covariance using our home sales example. Sum of squares xy is the numerator of covariance. It says we multiply each data point's x difference from x bar times its y difference from y bar. X minus x bar will be a number of x units, which for our example is square feet, and y minus y bar will be a number of y units, which is k dollars. The covariance formula says we multiply them, so the measurement units of covariance will always be the x unit times the y unit. That's straight from the formula. For our home sales example, this is square feet k dollars. Like variance, the units of covariance are often something unusual or non-intuitive, with no clear physical meaning. Whatever a square foot k dollar looks like is just a byproduct of the covariance formula. Here's our worksheet from earlier, where we calculated the covariance, and it was 92,018.1 square foot k dollars. The magnitude or size of this statistic, about 92,000, doesn't really tell us anything. It simply scales with the variances of x and y. If they're big, the covariance will be a big number, and if they're small, the covariance will be a small number. So the size of the covariance also has no physical interpretation. Now I'm going to tell you the simple treatment that will address both of these peculiarities at the same time. By peculiarities, I mean meaningless units and meaningless magnitude. Then I'll show you why it works, but if you follow along with me, it'll help you see how everything makes sense. Here's the thought process. We have these units of square feet and k dollars in covariance that we want to get rid of. Well, right here in our worksheet, we have those units for the x and y standard deviations. And we already said that the magnitude of the covariance is based on the magnitude of the two variances. So, I'll justify this in a moment, just bear with me for now. We're going to divide the covariance by the product of the x and y standard deviations. This isn't covariance anymore, so I'll remove this label. But I'll write it over here as the numerator of the fraction. Covariance divided by the standard deviation of x times the standard deviation of y. In our quotient, the square foot unit cancels out, and the k dollar unit cancels out. And we have 0.94962 with no units, all rounded up to 0.950. And this statistic is called the correlation coefficient. Its numerator is the covariance, and its denominator is the standard deviation of x times the standard deviation of y. I want to tell you three important things about the correlation coefficient. First, some of its many names, because it goes by several. Second, what it means and what it tells us. And third, some notes about its formula, where I'll explain why dividing by the standard deviation of x times the standard deviation of y works so well. The correlation coefficient has a long, formal name, but don't panic because nobody uses it. Pearson Product Moment Correlation Coefficient. This is what gets shortened down to correlation coefficient. Pearson was the mathematician who got credit for developing it. You might also hear Pearson correlation coefficient, Pearson's R with the lowercase r. He used the variable r in his papers where he introduced his findings, so mathematicians and statisticians who referenced it called it Pearson's R to avoid confusing it with other variables named r. Statisticians think he chose the letter r for relationship. Eventually, it became so prevalent and well known in the statistics community that the variable name lowercase r by itself has come to mean correlation coefficient. I'm making it yellow. R is a vocabulary word to know. You'll see the symbol r all through your statistics textbook, and it's referring to the correlation coefficient. So let me add r to our definitional equation. You may also see the functional notation COR, as shown here to mean correlation coefficient. Let me show you why it's such an important idea in bivariate data analysis. Most importantly, the correlation coefficient r answers our first two questions. Here's how. R will always be a number between -1 and 1. We'll talk about why in a few moments when we look more closely at its formula. If r is close to 0, then there's no linear relationship between the variables. A positive r means a positive correlation or an upward trend. A negative r means a negative correlation or a downward trend. Well, in this respect, the correlation coefficient is a lot like the covariance because the sign denotes the direction of the correlation, upward or downward. But unlike the covariance, the magnitude of the correlation coefficient answers question 2. The closer the value is to 1 or -1, the stronger the relationship. Let's show some examples. Here, all the points are on a straight line whose slope is positive. There's perfect correlation, and the correlation coefficient is +1. We'll see why when we talk about the formula. A correlation coefficient of 1 is extremely rare in the real world, and it's probably safe to say you'll never encounter a correlation coefficient r being exactly equal to 1, especially if your sample is large. There's always at least some variation, as shown here. There's still an upward trend, but the data points don't lie exactly on a straight line. The correlation is high, but not +1. Note that the trend line did not change. R changed, but the line didn't, so the correlation coefficient R does not tell us anything about the trend line, except its sign tells us if the slope is positive or negative. We'll identify the trend line when we learn regression. R just tells us how strongly the variables are related to each other, which means how closely they're packed around the best straight line. When the trend is downwards or negative, the correlation coefficient will be negative, and a value close to -1 denotes a strong negative correlation. Here's a weak negative correlation. Before I talk about the formula for the correlation coefficient R, I need to point out that if two variables are correlated, that does not mean that one causes the other. You'll see this in the correlation chapter of every statistics textbook. Correlation does not mean causation. Here's an often used example. Along the horizontal axis, I'll plot ice cream consumption, and along the vertical axis will be number of drownings. Each data point corresponds to a particular calendar month for a large metropolitan area. We have 24 points because we have data for 2 years. By the way, I made this data up. It is not real. We can see a clear correlation. In months with low ice cream consumption, there were relatively few drownings, and in months with higher ice cream consumption, there were relatively more drownings. So, does eating ice cream cause drowning? There is an obvious and clear correlation, but in this case, no causation, because both of these variables depend on a different variable related to temperature. In warm summer months, people eat more ice cream and they swim more, and more swimming means more opportunity for swim-related accidents. So, just because we observe a correlation between two variables, that doesn't mean that one variable causes or influences the other. People can be misled by claims like this, so be a careful student of data analysis. Correlation does not mean causation. Okay, back on track. I've mentioned the correlation coefficient's names and its meaning. Now I want to talk about the formula for R and why it's 1 when the correlation is perfect. I don't think you have to know this, but like everything else, if you can see what's going on, it can make everything so much more clear. Here's the formula for the correlation coefficient R. The numerator, the covariance, remember, is the average size of the yellow rectangles. Each rectangle is its points blue x difference times orange y difference, like this. We've already seen this several times. The denominator is the product of the standard deviations of the x and y variables. Now, I'm going to tell you this without proving it. When a data set's points lie along a straight line, the average area of the yellow covariance rectangles is equal to the product of the standard deviations. So, for data that fits a straight line, the numerator and denominator of R are equal to each other. So the quotient, the correlation coefficient R, is equal to 1. As the points deviate from a straight line, the product of the standard deviations increases relative to the average size of the yellow covariance rectangles. I'm exaggerating the change so you can see it. The yellow covariance rectangle is now smaller than S sub x times S sub y, so R is less than 1. Now, just to be clear, I've shown the yellow covariance rectangle shrinking and the two standard deviations growing to make the point, but in actuality, either can increase or decrease as data diverges from linear, but their size relative to each other will get smaller so that R is less than 1. The more scattered the data points are from a straight line, the greater the difference in the ratio, since the yellow covariance rectangle is getting even smaller relative to the product S sub x times S sub y. So R gets smaller and smaller as the data points diverge from a straight line. For negative slopes, perfect linear correlation yields R equals -1, since the covariance is negative. And as the points vary more and more from a straight line, R gets closer and closer to 0, but still negative since the covariance is negative. The formula for the correlation coefficient consists of 3 factors we already know how to calculate. The numerator is the covariance, the average product of x and y distances from the mean, whose memory aid is the yellow rectangle. The denominator is the product of the x and y standard deviations, S sub x and S sub y. The standard deviations are the square roots of the variances. When we combine these into a single expression, it can look overwhelming. I sometimes wonder how many prospective students have flipped through a statistics textbook, seen an expression like this, and decided they didn't have any interest in studying statistics. It's a real shame because each piece is a simple idea. They're all finding differences, squaring them, and summing them up. It's what statisticians seem to do most often. Please don't be put off by formulas. All of our formulas in statistics can be simplified using standardized, easy-to-understand symbols. Everything has a meaning and interpretation on the scatter plot. I want to encourage you to understand the meaning of each symbol and practice, and the formulas will be easy to understand, remember, and calculate. This expression can be simplified. Please notice these n-1 factors. There's 1 in the numerator and 2 in the denominator, but since the ones in the denominator are under a square root, their product is n-1, and they cancel with the n-1 in the numerator. So here's what's left after canceling the n-1. Now let's notice that the numerator is the sum of rectangles, but which we call sum of squares, xy. In the denominator, each radical contains a sum of squares for one of the variables, ss sub x and ss sub y, or xx and yy, same thing. So we can combine the terms under the radicals and get a new expression for R that just consists of sum of squares terms. I guess those statisticians were onto something by summing up all those squared differences, because it sure comes in handy. Can you see from the bottom formula how the correlation coefficient R is a unitless statistic? The units of the numerator are square foot k dollars, which is x unit times y unit, and the units of the denominator are the square root of x unit squared times y unit squared, which simplifies to x unit times y unit. So the units cancel, and R is just a number between -1 and 1 that reveals how closely packed the data is around the best fit line. Statistics packages will calculate the correlation coefficient R given x and y data elements. Before I show the Excel function, let me point out that we canceled n-1 from our formula, and so these two equivalent expressions for R don't reference the sample size. That'll be important in a second. And here's our worksheet with the correlation coefficient function added. It's called Correl, C-O-R-R-E-L. And like covariance above it, it needs 2 ranges for inputs, one for the x variables and one for y. Please notice that the correl function doesn't have a .s version for samples or a .p version for populations. Since the calculation can be made from sum of squares without dividing by sample or population size, the math is the same for samples and populations, so there's just one function, correl, to cover both. The correlation coefficient R for our home sale dataset is very nearly 0.95, indicating a strong positive correlation. Here's a summary chart for correlation coefficient. We've gone over all this already, so I won't repeat it, but here it is in one place. Now we're ready to address the last two questions, which involve making predictions about new data values. Question 3. Now that we have our second variable, square feet, can we make better predictions than simply predicting y-bar? Making predictions requires a mathematical model, and the model for data with a linear relationship is a straight line. With only one variable, our straight line was y-bar. But with two variables, we can have a trend line of some sort. We find the trend line using linear regression. Linear regression means finding the best fitting straight line through a series of data points on a scatter plot. So, what's the best fitting line? As you can see, we have an infinite number of lines to choose from. So, how do we decide which one is the best fitting? It might not surprise you to learn that the answer involves summing squared differences, specifically the differences between each data point and the modeled line. Let me show you. Let's assume that the purple line is our model and consider this data point. We're going to consider the distance between each data point and the purple model line. I mean the vertical distance, not the oblique shorter distance. We're always measuring distances parallel to our coordinate axes. Before squaring it, let's lock down our symbols and their meanings. I think that'll help make everything clear. The y value of our point is y sub 1, the y value of the first data point. Here it is, $271.7 K. It's the actual sales price we observed for a home whose square footage was 1,701. Now we need a symbol for this point, the y value that our model predicts for the same x value. In general, predicted y values on the modeled line have the label y hat. It looks and sounds strange if you haven't encountered it before. It's a y with a hat or caret symbol over it, and we say y hat. In statistics, the hat symbol over a variable means a predicted or estimated value. It can mean other things in other branches of math and physics, but in statistics it means predicted value. So when you see y hat, you can think predicted value for y, or if you're in a hurry, predicted y. And the predicted value for our first data point gets the symbol y hat sub 1. So the vertical purple bar represents a difference, and the general equation for its length is y minus y hat. Well, we're doing analysis on a scatter plot, and that means, as you might guess, when we see a difference, we're going to square it. Again, statisticians don't usually draw actual squares on their scatter plots, unless they're showing someone what the equations mean, which is what I'm doing for you. Every point gets a square whose sides have length y minus y hat. Some big, some small. The greater the vertical distance from the point to the model line, the bigger the square. The definition of the best fit line is the line whose squares have the smallest area. So you might hear linear regression called least squares regression, because we're seeking to minimize these purple squares when we choose our model line. And different model lines will have different squares. We want to describe a straight purple line, so let's talk about lines for a minute. Please remember from algebra that the equation of a line is y equals mx plus b. M is the slope, and b is the y-intercept. The y-intercept b is just what it sounds like, the point where the line intercepts the y-axis, which is the same as the y value when x is 0. The slope is the vertical rise or fall per unit change in x. You've probably heard slope called rise over run in algebra. Now, the equation of a line for simple linear regression is written a little differently. First, the y value our model generates is going to be predictions for y, not actual y values. So to be precise, we must start the equation with y hat instead of y. Then, I'll explain why in a moment, they flip the right side around so that the y-intercept is first. And in statistics, the y-intercept is not usually called b, it's called a. Sorry, I'm not responsible. So the slope term comes after the y-intercept. But there's one more change. In the equation for the linear regression line, the slope is not called m, it's called b. And this can get a little confusing because in algebra, b usually means the y-intercept, not the slope. Just note that the coefficient of the variable is always the slope. We'll use the linear regression format going forward. Let me show you an alternative you might encounter with multiple regression. I'm not covering multiple regression in this video, but I want you to know what it is. In multiple regression, there's more than one independent variable used to model the dependent variable. For example, to predict the sales price of a home, we might consider the square footage and the number of bedrooms and the number of bathrooms. Multiple regression models have this format. Y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2, and so on for however many independent variables are included. The first term is b sub 0, also called b naught, since naught, N-A-U-G-H-T, is another word for 0, and it's easier to say. B naught is the y-intercept. Then additional bx terms are added, one for each independent variable. When analysts are working on multiple regression, they include and exclude different variables as they refine their model. So the regression equation gets longer and shorter based on the number of variables included, and subscripts let us label them clearly. That's why the y-intercept comes first, so all the independent variables and their coefficients, however many there are, can be strung together at the end. If the y-intercept was last, its subscript would change based on how many independent variables were being considered. But when it's first, the y-intercept always has the symbol b naught. So, even in simple linear regression with only one independent variable, it's still okay to see y hat equals b naught plus b sub 1 x. It's just the multiple regression format with only one independent variable. So you might see this too, and now you know where it comes from. There's just one more version you might see, and that's using the Greek letter beta instead of lowercase b. Ordinarily, Greek letters are used for population parameters, and Latin or English letters are used for sample statistics. But in regression analysis, the distinction is sometimes blurred since our model is based on a sample, but we're trying to model the population. Please don't be confused. For simple linear regression, it's just the equation of a line with a y-intercept and slope. I'll use a plus bx for the rest of this video. So here's the equation of our model line. Y hat equals a plus bx. It will let us predict the value for y given a value for x, or it will once we know the values of a and b. Remember, we want the values for a and b that result in the line that minimizes the sum of squares y minus y hat squared. So, what values for a and b describe the best fit line? The method to derive the formula for b depends on calculus and isn't particularly interesting, but the results are extremely interesting and satisfying. As it turns out, the slope of the best fit line, b, is a fraction made from sums of squares. The numerator is the sum of squares xy. The denominator is the sum of squares x. So we can find the slope of the best fit line using statistics we already know how to calculate. In order to find the y-intercept a, we need one more piece of information, which I'll tell you without proving it. The best fit line will always pass through the centroid. This is valuable information to know. When you plot a best fit line on a test or homework problem, you can double-check your plot accuracy by ensuring the line intersects the centroid. So, how can we use this information to find the y-intercept a? Here's how you might think about it to remember the formula. We know the slope from our sum of squares, so we have a line at this angle, but we don't know where it should be. But since we know it passes through the centroid, the coordinates of the centroid must satisfy the line's equation. So we can plug them in. Y bar equals A plus B x bar. Since we'll know x bar, y bar, and the slope b, we can rearrange to isolate the y-intercept a. And this is how we find the y-intercept. We know the slope and 1 point on the line, so plug those into the equation for the model line and we can solve for a. Easy. Since the slope b is in the equation for y-intercept a, we must find the slope before we can find the y-intercept. Now, let's focus on our units of measure for a moment. I want you to see that everything balances out and that units are worth our attention. In fact, if you ever forget or confuse two statistics, you can often use the units of measure as a way to remember the correct formula or compare alternatives. Let's use our geometric memory aids on the scatter plot to recall that the sum of squares xy is the sum of all the yellow rectangles, and the sum of squares x is the sum of all the blue squares. The yellow rectangles have units that correspond to the product of the x and y units. You can see that right on the memory aid, x units times y units. The blue squares have units that correspond to x squared, x units times x units. An x unit cancels from the numerator and denominator, leaving us with y units divided by x units for the slope. And this makes sense and is what we'd expect. The slope is rise over run, the ratio of the change in the y variable per change in the x variable, y over x. Perfect. Now for the y-intercept. The unit of measure of y bar is the y unit. The unit of measure for slope b, we know from above, is y units divided by x units. And the factor x bar, of course, carries the x unit. In the right factor, the x units cancel, which leaves us with y units minus y units, which is, of course, y units. So our formula for the y-intercept yields a measure whose unit is the y measurement unit we'd expect, so everything balances out. Once more, units are important. They can aid our understanding and help with interpreting results. And I found that if I got confused or uncertain as to which of two formulas to use for a statistic, or if I was supposed to square something or not, or take the square root, thinking about the expected units of measure could help me choose the correct formula. Please don't ignore units. They can be like a cheat code to help learn, visualize, and understand, and they're right there on your scatter plot. I've already alluded to this point, but I want to state it clearly. Outside of school, these calculations are not performed manually. Analysts use statistical packages to do the tedious calculations. And in this video, I'm using Excel to show you how easy it is to get statistical results. And in just a moment, I'm going to show you how to use Excel to find the slope and y-intercept of the best fit line. But be careful. It's possible, even easy, to learn how to use statistics packages without really understanding statistics. But it's more important to understand statistics than to know how to use a particular statistics package. For example, an employer who uses a statistics package you don't know will still hire you if you're a good statistician. If you know statistics, they can teach you their package in a week, but they cannot make you a good statistician in a week. Easy access to easy-to-use tools can be a shortcut to becoming a poor practitioner of your art or science, no matter what your art or science is. A relatively simple goal here is to be able to calculate correlation and linear regression statistics on your own, at least for a small sample, and be able to explain each metric and statistic to a younger student, and draw them and identify them on a scatter plot. At the end of the video, I'll provide a complete walkthrough with a new set of data to show you what I mean. Okay, I'm done. I'm just encouraging you to be a diligent and enlightened student, no matter what you decide to study. It's better to understand than to memorize. All of my videos have visualize in their titles because I think seeing can help in understanding. So, let's find the slope and y-intercept of the best fit line for our home sales data. The slope b is sum of squares xy divided by sum of squares x. When we found covariance, we made this chart and found sum of squares xy right here, 460,090.5 square foot k dollars. It's the total signed area of all 6 yellow rectangles. I'll remember it so you don't have to. And when we found the variance and standard deviation of variable x, we made this chart and found sum of squares x right here, 3,650,754 square feet squared. And so, plugging in, we get a slope b of 0.1260 k$ per square foot to 4 decimal places. Of course, the slope has an interpretation right here on the scatter plot. Airplane, dang it. For every increase of 1 x unit, which is square feet, the predicted y-hat value increases by 0.126 y units, which are k dollars. Since 1 k dollar is $1,000, our model predicts that the home sales price will increase by $126 for every additional square foot. That's what the slope means and how to interpret it, our predicted change in y per unit change in x. For the y-intercept A, all we need is x bar, y bar, and the slope we just found. I'll plug them in and we get 69.36 k dollars. Now that we know the slope and intercept, we know the equation of the best fit line by plugging in y hat equals 69.36 plus 0.126x. Once you know the y-intercept, it's easy to draw the best fit line on the scatter plot, since it passes through the y-intercept and the centroid. Let's use our best fit line to make a prediction. How much might we expect to pay for a new town home whose size is 2,400 square feet? We only need to plug x equals 2,400 into our y-hat equation, and we get 371.76 k dollars. Of course, the regression line tells us the same thing, since it's a graph of the equation we just used. We need to be careful when we make predictions. Here's the data we used to make our model. We only had sales prices for homes between 1,701 and 3,946 square feet. Our model might be applicable to smaller and larger homes that are outside of our observed X range, but we can't be certain. It's not a good idea to use a model to make predictions for values outside the values used to create the model. When we make predictions for models inside the range, that's called interpolation. Interpolation is safe, and it's what we built our model for. When we make predictions for values outside the range, that's called extrapolation. Extrapolation is risky and should be done with care, if at all. For example, I might use the model to predict the sales price of a 1,650 square foot home, since that's very near the observed range. But I would be reluctant to predict the price of a 900 square foot home with this model, since that's relatively far from our observed range. Similarly, the sales price of a 25,000 square foot mansion should not be predicted with this model. Just remember that the model we come up with is only good for the data range we used to develop it. The vocabulary words are easy to remember because interpolation is internal to the observed range and extrapolation is external. Okay, let's see how to get the slope and y-intercept of the least squares regression line using Excel. There's a function named slope that takes the two ranges as inputs, but please be very careful because in Excel, the slope function assumes the y variable range is first and the x variable range is second. Be sure to check the documentation of your statistics package to see which comes first. Another function, intercept, will return the y-intercept A of the best fit line. Excel's answer for the y-intercept is slightly different than ours because I rounded the slope b to 4 decimal places before computing A. Neither of these functions has a .s or .p version since the slope is calculated using sum of squares without dividing by n or n-1. So the math is the same for samples and populations. And we're making progress. We now have the answer to 3 of our questions. For number 3, our improved prediction is based on the least squares regression line, y hat equals a plus bx. The last question is, how good is the prediction? This one's going to require some important new vocabulary for concepts we've already covered. When looking at our 6 home prices, we see upwards and downwards variability around the mean. But why aren't all the prices the same? Why aren't they all closer to the mean? There must be some explanation for the variability. We've explained some of the variability by including the home size in square feet in our model. But how much of the variability have we explained? We need a way to keep track. By this time, it probably won't surprise you to know that we're going to use sums of squares to measure the effectiveness of our model. Our simplest and worst prediction is simply y-bar. It's worst because it doesn't take advantage of the explanatory variable home size in square feet. So y-bar is our baseline. As usual, let's square these distances to y-bar. It looks like 5 squares instead of 6 because this one was too small to see, remember? It should all look familiar. We've already done this, and the sum of the orange squares is sum of squares y. The sum of all the squared, y minus y-bar. Well, we came up with a model to try to explain the variation. The purple line we found using least squares regression. Now we'll find and square the distances from each point to the purple prediction line. So instead of subtracting the mean, y-bar, we'll subtract the prediction, y-hat. Of course, this purple sum will be smaller than the orange. In fact, we used least squares regression to find the purple line that would make the sum of all the purple squares as small as possible. In the context of regression, these two sums of squares get new shorthand names and abbreviations. The orange is called SST for sum of squares total. It's the total variability we're trying to explain with our model, and is the same as sum of squares y. Within the context of covariance and correlation, we called it sum of squares y, and in the context of regression, we call it SST. It'll make more sense in a moment. The purple sum is called sum of squares error, or SSE, and I need to say immediately that in statistics, the word error does not mean mistake. Error refers to variability in the data that our model does not explain. So please think of error as leftover variability, not as a mistake. And unless all your data points lie on a perfectly straight line, you'll always have error because there can't be a straight line that passes through every point. So don't think it's your responsibility to get rid of all the error. Error, that is variability, is always with us. There's an important mathematical relationship between these sums of squares. SST equals SSE plus SSR. Well, I haven't told you what SSR is. Of course, it's more squares, and scatter plots can get cluttered and confusing when you actually draw a lot of squares. So let me focus first on this one data point. It's our second point, left to right, so I'll label its y value as y sub 2. Its predicted value is y hat sub 2 on the purple line, here at the same x value, which is 1,893 square feet. The mean is y bar here. Y bar doesn't get a subscript because there's just one mean, and it's the same for all the data points. We've already drawn the orange square, y sub 2 minus y bar squared, and the purple square, y sub 2 minus y hat sub 2 squared. There's just one more square we can draw with these 3 points, and that's based on the distance between the prediction, y hat sub 2, and the mean, y bar. And the sum of these green squares is SSR, sum of squares regression. It's the amount of variability in home sales price that's explained by our regression model. I want to point out something that tripped me up when I was in school, and I don't want it to trip you up. This sum of squares equation tells us that orange equals purple plus green. But if we look at our squares for our sample point, we can see that orange is obviously not equal to purple plus green. I don't think I ever got past this in school. I trusted the equation because it seemed to work every time, but I didn't see how it matched with what I saw on the scatter plot. The explanation is that it's only true when you sum up all the squares for all the points. For our sample point 2, the green regression square is the largest. For other points, like number 6, the orange total square will be the largest, and for point number 5, the purple error square will be the largest. But across all the data points, the 6 orange squares added together will always equal the 6 purple squares plus the 6 green squares. And that equality is only true when y hat is based on the best fitting least squares regression line. If you make up your own purple line or eyeball it, then SST will not equal SSE plus SSR. It's only true for the least squares model. Okay, I've got bad news and great news. The bad news is you've got to know these formulas for regression. The great news is you don't have to memorize them. You can, I guess, but I never did. Instead, I simply understood what each of these meant. Let me block out each difference expression and guide you through the thought process. SST, sum of squares total. That's the total variation before we even know y hat. It's the square of the orange lines from each data point y back to the mean. So y minus y bar. Check. By the way, since we're squaring all the differences, you don't have to remember whether it's y minus y bar or y bar minus y. You'll get the same sum for SST either way. Same with SSE and SSR. The order doesn't matter. Now for SSE, sum of squares error. That's the bit left over from our model, the difference between each actual data value and the prediction y hat. So y minus y hat. Check. SSR, sum of squares regression. That's the jump from our bad model, y bar, to our better model, y hat. So, y hat minus y bar. Check. Have I told you yet that it's better to understand what's going on than to try to memorize something you might forget? Let me rearrange the sum of squares equation so that it kind of reads left to right. The total variability, SST, is equal to the variability explained by a regression model, SSR, plus the remaining error not explained by the model, SSE. So the proportion of the total variability explained by the regression model is SSR divided by SST, and this ratio is called the coefficient of determination, our last major new metric for simple linear regression. Since SST equals SSR plus SSE, you'll sometimes see the coefficient of determination expressed as 1 minus SSE over SST. The proportion of the total variability explained by the regression model is 1 minus the proportion that's not explained. Of course, it's the same value. The coefficient of determination has some things in common with the correlation coefficient, so let me show you a chart. I don't want to stop and go over it, but I'll make a few points to compare them, and you can pause if you'd like to review. It's worth taking care because I remember being confused as a student, since both metrics had the word coefficient in them. But I hope you don't have the problems I did. Understanding and practice are the keys to defeating confusion and lack of confidence. On a scatter plot, the correlation coefficient R tells us how closely packed the data is about a straight line. Here's a small example with R equals plus 0.97, a very high positive correlation. Well, if the data is packed closely around a straight line, then that line will be our regression line, and since it's tightly packed, most of the variation from the mean will be explained by the regression model, and green SSR will be very close to orange SST. So if the correlation coefficient is high, the coefficient of determination will be high. They kind of seem to measure the same thing. And as it turns out, the coefficient of determination is always equal to the correlation coefficient squared. And the symbol for the coefficient of determination is indeed R squared. You'll see R squared all through the regression chapters of your textbook. In our example, R is positive 0.97, so R squared, the coefficient of determination, is 0.94, rounded. 94% of the data's variability from the mean is explained by the purple regression line. The remaining 6%, the leftover error, is not. Excel has a function for R squared called RSQ. Like the Corel function, it also expects the Y range first, then the X range. If there was no RSQ function, you could of course find R squared by squaring the results of the Corel function, since the coefficient of determination, R squared, is indeed the square of the correlation coefficient, R. For any data set you make up, you can find easily in Excel that the square of R is equal to R squared. But none of my textbooks proved it, and I couldn't find a video with the proof, so for the sake of completeness, I'm going to show a proof here. I'm not saying it's an elegant or efficient proof, and I don't think you need to know this. In fact, I'm sure you don't. I won't step through the details, but you can pause if you're interested, and I'll keep going. The last topic I want to cover before we evaluate a new data set from beginning to end is residual analysis. The residuals were the purple segments we squared to get SSE, sum of squares error. I didn't want to call them residuals earlier because of the possibility of confusion between green SSR and purple SSE. SSE is sum of squared error, and SSR is sum of squared regression. In an unfortunate twist of unhappy coincidences, we can describe SSR as explained variance, which may be confusing because the word explained starts with the letter E, even though it refers to SSR. And it gets worse. We could accurately describe SSE as the sum of squared residuals, which may be confusing because the word residual starts with the letter R, even though it's referring to SSE. So to avoid confusion, use the terms correctly and even say them out loud when working out sample problems. The idea behind residual analysis is that we can treat residuals like new random variables and plot them like this against the new horizontal axis. Ideally, there should be no discernible pattern, and the residuals will be distributed randomly above and below the model line. This is a characteristic of data that's well described by a straight line. Here's an exaggerated example where that isn't the case. The data is pretty clearly not described by a straight line, but we can, unwisely, fit the best straight line through it using our regression techniques. When we plot the residuals, we can see a clear pattern, which tells us that a straight line model does not fit the data very well and will not give us good predictions. Residual analysis is much more effective with a very large data set, since with small sets like this, you might see patterns where there really are none. The important takeaway is that correlation and linear regression analysis techniques are not smart enough to know whether they should be applied to a particular data set. That's our responsibility as data analysts, and you should make it a habit to visually examine every data set before applying any of these techniques. We'll do that together in the next worked out sample problem. Before we walk through a new problem set, let me illustrate a high-level map of our journey from beginning to end. Everything has a meaning on the scatter plot, and I'll point it out as we go. I'd guess this would be the part of the video that you would bookmark to review. We have a data set of n observations, blue x values and orange y values. Let's always start with finding their means, x bar and y bar, because most of the differences we'll square are differences from the means. We sum them up and divide by the sample size n, and that tells us x bar and y bar. On the scatter plot, here's the dotted line representing x equals x bar, and here's y equals y bar. Their intersection is the centroid, whose coordinates are x bar, y bar. I'm using a red outlined yellow square to represent the centroid so we don't mistakenly think it's one of our data points. I'll put it up here between x bar and y bar, just a visual reminder that the centroid is at coordinates x bar, y bar. The next step is to use x bar and y bar to find the differences, the x distance between each point and x bar, and the y distance between each point and y bar. We don't have actual values now, I just want to show you the natural sequence behind the thought process. If you can review this and repeat these steps in your head, I think that would be tremendous progress towards mastering the topic. Down in the scatter plot, here's a reminder of the meanings of these differences. X minus x bar is this blue horizontal distance from each point to x bar. I'm just showing one, not all. And y minus y bar is this vertical distance from each point to y bar. I'll add our visual aids to the top of the columns. Next comes the squared differences. The first, x minus x bar squared, is the x difference squared. On the scatter plot, it's represented by the area of the blue squares. Next is y minus y bar squared, the orange y difference squared. On the scatter plot, it's the area of the orange squares. Finally, x difference minus y difference. On the scatter plot, it's the area of the yellow rectangles. I'll add their visual aids to the top of their columns. Now, we can add up the squared differences to get our sums of squares. The sum of the blue squared x differences is sum of squares x, or equivalently, sum of squares xx, as I've shown it here. The sum of the squared y differences is sum of squares yy. Remember, from the topic of linear regression, we also call this sum SST, sum of squares total. It represents the total variance that our regression model will seek to explain. And the sum of the yellow rectangles is sum of squares xy. Of course, we realize we're summing up rectangles, not squares, but we still call it sum of squares SS so that it fits the pattern. Now, remember that the variance of x is the average of the x differences. To find the average, we take the sum and divide by how many. And we have the sum right here, sum of squares x. We divide by n minus 1 because the variance based on the sample is a biased estimator of the true population variance, and dividing by the smaller number, n minus 1, bumps up the variance so that it better estimates the population variance. And that's the variance of x, s sub x squared. When we found x bar and y bar, we divided by n because the sample mean is an unbiased estimator of the population mean. So we can just take the average as normal and divide by n. But when calculating variances and covariances, we need to divide by the sample size minus 1, and we still call it average. The variance of y is the average of the squared y differences, s sub y squared. The square root of the variances are the standard deviations, s sub x and s sub y, not squared. The average of the sum of squares xy, remember, is the covariance, which has strange units, so we normalize them when we divide by the standard deviations of x and y to get the correlation coefficient r. Now we're ready for the regression statistics, where we'll find our best fit line we can use to make predictions. Y hat equals a plus bx, where a is the y-intercept and b is the slope. We find the slope first. Slope b is sum of squares xy divided by sum of squares xx. The y-intercept is y bar minus b times x bar. X bar and y bar are the coordinates of the centroid, so once we know the slope, we use the centroid to find the y-intercept. And now we can put the best fit regression line on the scatter plot. It will always pass through the y-intercept and the centroid. Using the regression line, we can calculate y hat for each x value. We just plug each of the x variable values into our regression line to get the values for y hat. All the y hat values lie on the regression line, and I'm showing them as purple points on the scatter plot. Next, for each data point, we calculate two distances from y hat. First, the difference between each actual y value and the predicted value y hat, so y minus y hat. These were the purple residual lines not accounted for by the prediction model. I'm showing one on the scatter plot for the rightmost point. It might be too small to see. It's the distance from the actual white point to the predicted purple point. That's y minus y hat. And as usual, we square these differences, y minus y hat squared. Here are the visual aids. When we sum up the purple squares, we called it SSE, sum of squares error. Error means variability not accounted for. It doesn't mean somebody made a mistake. There will always be some variability in your data, so there will always be at least a little error, sometimes a lot of error. Error depends on your data, not on you, so don't let it bother you. The second difference using y hat is y hat minus y bar. On the scatter plot, it's the pale green distance from the mean y bar to the purple predicted value y hat. I'm just showing one. Squaring these differences gives us y hat minus y bar squared. Here are the memory aids. When we sum up the pale green squares, we call it SSR for sum of squares regression. It's the amount of the total variability, SST, accounted for by the regression model. So the proportion of the total variance explained by the regression model is SSR divided by SST. This is the coefficient of determination, whose symbol is r squared, and whose value is indeed the square of the correlation coefficient r. And this picture captures the details of correlation and simple linear regression. If you can step through this process and see how everything has a meaning on the scatter plot, you'll have a much easier time than someone who doesn't see the whole picture. I'm going to work through a new problem using this format as a template. Here's our new data set. We asked 8 university students for their screen time in hours for the week before their final exam and collected their corresponding final exam scores. So our data is screen time versus final exam score. And full disclosure, I made this data up also. I said earlier that we should review a scatter plot for our data before doing any analysis. So let's see how to do that easily in Excel. First, we enter, paste, or import our data into adjacent columns like this. Then we highlight the range by left-clicking the upper left corner and dragging to the lower right-hand corner and releasing the mouse button. That should highlight all the cells in the dataset. Then click the Insert button. In the Charts section, click this drop-down. Then click the first Scatter option. This will put a very simple scatter plot on your worksheet to give you an opportunity to visualize the data relationship, if one exists. It's not a scatter plot you'd want to include in a report or paper. It doesn't have a title or axis labels. You can use Excel options to make it more presentable, but it's a quick and easy way to examine your data. Once you highlight your data, it's a simple 3-click process, and you should do this every time. Our data set looks like a good candidate for a linear model, so we'll proceed. I'll transcribe the x and y values in our data set. We'll add them up and divide by 8 since there are 8 observations. To get the means, x bar is 12 hours and y bar is 78 points. These correspond to the coordinates of the centroid of our data set. For every statistic, I'm going to state the units of measure even if I don't display them in this chart. The x unit is screen time in hours. The y unit is exam score points. Now that we know the means, we can calculate each point's distance from the mean. The first x value is 4 hours, and x bar is 12 hours. 4 minus 12 is negative 8 here. The first data point is 8 hours below the mean. And we subtract 12 from all the other x values. They all represent a number of hours above or below the mean of 12 hours. And on the scatter plot, we draw them as horizontal blue lines from each point to x bar. The first y value is 88 points, and y bar is 78 points. 88 points minus 78 points is 10 points here, and we subtract 78 points from all the other y values. They all represent a number of points above or below the mean of 78 points, and on the scatter plot, we drew them as vertical orange lines from each point to y bar. It should be pretty easy to remember what comes next. In statistics, once we find the difference between two numbers, we almost always square it, because we're going to need the sums of squares. For the first point, we square x minus x bar, which is negative 8 hours. Negative 8 hours squared is 64 hours squared, so 64 here, and we square all the other x minus x bar values. They all have units of hours squared, and on the scatter plot we drew them as blue squares constructed on each blue horizontal line. Likewise, since y minus y bar is 10, y minus y bar squared is 100 here, and we square all the other y minus y bar values. Their unit of measure is exam score points squared. On the scatter plot we drew them as orange squares constructed on each orange horizontal line. For the next column, we take the product of x minus x bar and y minus y bar. That's negative 8 times 10, so negative 80. And we find the product for all the other data points. The units for this column are hours times exam score points. On the scatter plot, we drew them as yellow rectangles having the blue and orange differences as their sides. We sum up these squared values to get our sums of squares. SS sub xx is 203, the total area of all the blue squares, whose unit of measure is hours squared. Sum of squares y is SS sub yy, which is 640, the total area of all the orange squares. Its unit of measure is y unit squared, which is exam score points squared. In regression analysis, sum of squares y is often called sum of squares total, or SST. It's the total variability in y that our regression model tries to explain. Sum of squares xy is negative 306, the total area of all the yellow rectangles. Its unit of measure is x units times y units, hours times exam score points. As we'll see in a moment, sum of squares xy is the numerator of the covariance statistic. Now we can find the variances, since the variance is just the average of these squared areas. So we divide the sum of squares by 7, one less than the number of observations n. The variance of x, s sub x squared, is 29 hours squared. Its units are the same as sum of squares x, since we're just dividing by 7 to get the average. Dividing by a unitless number doesn't change the units. The variance of y, s sub y squared, is 91.4 exam score points squared, the same unit as sum of squares y. And when we divide sum of squares xy by n minus 1, we get the covariance, which is negative 43.714, whose units are hours times final exam points. Covariance has the same unit of measure as the sum of squares xy, x units times y units. Since the covariance is negative, we know that there is a negative or inverse relationship between the x and y variables. In our case, as screen time increases, the final exam score tends to decrease. Once we know the variances, we can find the standard deviations by taking the square root. The variance of x is 29 hours squared, so the standard deviation, s sub x, is the square root of 29 hours squared, which is 5.39 hours. The unit of measure of the standard deviation of x is always the x units. The variance of y is 91.4 final exam points squared, so the standard deviation, s sub y, is the square root of 91.4 final exam points squared, which is 9.56 final exam points. The units of measure of the standard deviation of y is always the y units. For covariance, whose units are x units times y units, we divide by the product of the standard deviations we just calculated to get the correlation coefficient r. The units of measure cancel out, so r is a unitless measure between -1 and 1 that tells us the direction and strength of the relationship between the variables. For this case, -0.849 denotes a relatively strong negative relationship. The next column is y hat, our predicted value for y, but we need a model to make predictions, so first we need to determine the best fit line. The slope b is sum of squares xy divided by sum of squares x. We know both numbers, so we plug them in to get a slope of -1.51. The subscripts on the sum of squares in the fraction can remind us of the units of measure. An x unit cancels, leaving us with y unit divided by x unit, which corresponds exactly to the definition of slope. So, with units, the slope has a meaningful interpretation. The slope is -1.51 exam points per hour, which means the trend is that every hour of screen time is associated with a reduction in the corresponding exam score of 1.51 points. Now we need the y-intercept a, which is equal to y bar minus b times x bar. B, remember, is the slope we just found, -1.51. When we plug in the numbers, we get 96.12. The units of measure of the y-intercept are exam points. So our best fit line is y hat equals 96.12 minus 1.51x. On the scatter plot, this corresponds to the purple regression line, our prediction model. And now we can fill in the values for y hat using the prediction model. Our first x value is 4, and we plug this into our y hat equation. 96.12 minus 1.51 times 4 equals 90.06. There may be rounding discrepancies. I'm carrying extra digits behind the scenes. Likewise, we fill in the other y hat values. On the scatter plot, each prediction value y hat corresponds to a purple point on the purple regression line. Now we're ready to fill in our error amounts, the variability in our data not explained by the model. This is y minus y hat. On the scatter plot, it's the vertical distance from each white data point to the purple point predicted by the model, as shown by the purple line. For this sample point, it's pretty small. On our data grid, it's each y value minus the corresponding y hat. For the first point, y is 88 and y hat is 90.6. 88 minus 90.6 is negative 2.06 here. And we subtract all the other y hat values from the actual y value to get the variability in our data that the model does not explain. As usual, we square these differences. On the scatter plot, they're the purple squares constructed from the purple lines. Again, pretty small on our scatter plot. Summing all these purple rectangles gives us SSE, the sum of squared errors, which for our data set is 178.4. The units are the y unit squared, so exam score points squared. To finish our chart, we calculate y hat minus y bar. This is the vertical distance between the mean and the corresponding regression model prediction for each x value. Y hat is in this column and y bar is always 78. So for the first data point, 90.6 minus 78 is 12.06. It's a vertical difference, so the units are exam score points. On the scatter plot, this is the pale green distance from the mean to the corresponding purple prediction point. And we can fill in the rest of the differences by subtracting 78, y bar, from each y hat. As is our habit, we'll square these differences and sum them up to get SSR, sum of squares regression, which is the total area of the pale green squares. It's the amount of the total variation explained by the regression model. So for the units, these are, again, y distances squared. The y distance is exam score points, so the unit of measure of SSR is exam score points squared. And now we can calculate R squared, the coefficient of determination, as SSR divided by SST. We just calculated SSR here, and SST is the total variation in y over here, sum of squares YY. 461.26 divided by 640 is 0.721. So for this data set, the best fit straight line based on screen time explains 72.1% of the total variation in exam scores. You can double check your work by verifying that SSE plus SSR equals SST, and that the coefficient of determination, R squared, is equal to the square of the correlation coefficient R. This material isn't really difficult, and I would encourage you to practice a few times until you can build this chart from scratch for a small sample of 6, 7, or 8 data points using only a calculator. Put unit labels everywhere, and make sure you understand how every single statistic has an actual meaning on the scatter plot. If you're in a study group, I'd suggest that everyone in the group make up their own data set and calculate these statistics. Then share them so everybody gets to practice using everyone else's problems. Here's one more problem. I won't work it out, but I'll show the statistics in a moment. We've measured the reaction times of 7 senior citizens at a retirement center. We've recorded their age in years and their reaction time in seconds. Here's the data set. Like we did for the last example, calculate and show your work to find x bar and y bar, the sums of squares, the variances and standard deviations of x and y plus their covariance, the correlation coefficient R, the regression statistics, slope B and Y-intercept A with the resulting equation for the best fit line, all 7 y hat values, the sums of squares regression and error, and the coefficient of determination R squared. These requirements make a good checklist for your review. You should know what everything means, alternate names or descriptions, how to calculate it, and what it represents on the scatter plot. You will be well poised for success if you practice until this becomes familiar, and it'll just take a few problems like this. Here are the results in the format we've been using. Please pause or screen capture if you're interested. And for review, here's another summary of the checklist with units. With practice, there should be nothing mysterious on this chart. Before I wrap up, let me insert a personal note. I've recently retired from full-time employment. I've never been a fast YouTube content creator, and this past year I've slowed down even more because I've been doing and enjoying retirement things. But I will get back to making videos. I try to make the instruction fast-paced, so if you thought it was worth your time and want to see more, please like, subscribe, and share with your colleagues. Statistics is a very broad topic, one that I enjoyed a lot in school, and I hope you do too. Bivariate data analysis is a relatively small but important subset of statistics. Our 2 variables can be combinations of categorical or numeric, and when both are numeric, we can visualize them on a scatter plot and use the analytical methods covered in this video. These analysis techniques can be extended to more than 2 variables. I don't cover multivariable topics in this video, but it's still a solid foundation for more advanced concepts, and your familiarity with the subject matter will serve you well in your future studies. I'm Dennis Davis. Thanks for watching.